the tutorial today is about chapter 4 and chapter 5. So basically chapter 4 is about differentiation of functions, and chapter 5 is more about, I think, the mean value theorem. So we can start with chapter 4. So let me share my screen and we can have a little look at what's going on. So this is a tutor-led tutorial. So I'm going to be sort of stepping you through the problems. So this is page 82 in the booklet. And, you know, you can see the first few questions are find derivatives and all that sort of stuff. I'm going to start with question 3, which is a hard one, but actually I'm not really sure why this is a hard one, maybe because it involves limits. But if you take a graphical approach to this question, it's pretty easy what's going on, right? So we've got this function here, which is the product of x with the absolute value of x, okay? And you're asked to compute these limits if they exist, and then state the value of the derivative of the function at x equals 0 or why it's not differentiable, okay? Now, in many cases, as I'm sure you already know, drawing a picture can help, okay? Did someone say GeoGebra? Well, let's go and have a look. So what I've done here, let me share my GeoGebra screen with you. So you should be able to see that now. I've just plugged in this function. I've called it G here, right, instead of F, because I've already assigned F somewhere else. But you can see from that picture, it's basically two curves posted together. This is the x squared curve on the right-hand side of x equals 0, and this is negative x squared. So you've sort of cut them and pasted them together, and the question is, do the derivative, I guess the third question here is, does the derivative exist at x equals 0? So from that picture, who can tell me in the chat, is that function differentiable at x equals 0? Is that function, I know it's early on a Monday morning in Sydney, is that function differentiable at x equals 0? Okay, there's some no's, there's some yes, 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 yes from Dharam, thank you. Okay, so for those who've said yes, okay, good, Rahul, let's see if you can put in a justification why. So I agree with you, it is differentiable at x equals 0. Why is it differentiable at x equals 0? Now, Rahul says because it's continuous, I think, although I'm not convinced by that. Can anyone say something maybe a bit more geographic, sorry, a bit more graphical, or some other way of justifying why it's differentiable at x equals 0? Smash that chat button. If you were justifying this, how might you do it in an informal way? All right, Dharam, it's continuous, and the limit from the right equals the limit from the left. Yeah, have to be a bit careful with continuity and differentiability. So I'm not 100% sure about that. Marley says it's because the left-hand limits of the function are equal. Again, not necessarily, right? If I was to put in this function here, right? Let's say that function's continuous, but it's not differentiable because it's got a corner, right? So need to be careful. All right, Julia is on the case. It's smooth and continuous. Okay, well, I think just smooth is enough, right? It's a nice smooth curve. There's no corners or jumps or whatever. And Matthew says that you can draw a tangent line. Yes, you certainly can. Okay, so I would say looking at the curve and the graph of the function, it's what's known as a nice smooth curve, and a smooth curve is always differentiable. All right, so then what would the derivative be at x equals 0? What actually is what like from the graph? Who can tell me what is the derivative at x equals 0? All right. So I think I would just look at Matthew's earlier comment. You can draw a tangent line. That tangent line is going to be horizontal, so the tangent line has a slope of 0. So you're all correct. Okay, so we know where we're going. Let me stop sharing now. So we know where we're going. We can draw the graph easily, right? Especially with Maple or GeoGebra. Let's compute the question by hand, and we can press on. So let me share my document camera with you. I'm loving the chat, by the way. Okay, here we go. I'm back on the Sharpies today, so you should be able to see that. All right, so this is question 3 in chapter 4, and we've got a function which is defined in the following way. Okay, and just for completeness, I'm going to break up that absolute value so we can x times negative x. So this is the case when x is, say, greater than or equal to 0. So we just basically split up the absolute value into positive x or negative x, depending on where we are. Okay, so this is exactly what we had in our graph on GeoGebra the other day. Two different parts of a parabola stuck together. Okay, so part A asks us to compute the following limit. Now we know it exists, right? Because we've actually been able to work this out from the graph. So we know where we're going, and we actually know that this is going to be equal to 0. Okay, so this is just the limit definition of a function, the limit definition of the derivative of a function at 0. So in this case, h is positive, so this bit's going to be positive. So this will be our function here. Okay, it's not this part, it's this part. We're coming in from the right. So this will just be h squared. At x equals 0, our function is just 0 squared. And then we get, oh, h on the bottom, sorry, I need to put a little limit in there. There, I've just squeezed that in. Okay, so we can cancel off the h's, and it's pretty easy. So the limit, as we already know, is going to be 0. Okay, so the limit does exist, and it's equal to 0 from the right. So let's do the left-hand limit. It's going to be very similar. So all we need to do now is realize that here we're going to be to the left of 0. So this is going to be my function for the first part. Minus f of 0, which is going to be here, so 0 squared. So you'll, so I've left off the limit again. Sorry. Okay, so you're going to get the cancellation, and that's going to go to 0. So as we expected, these two limits are going to be 0. And that then tells us, so that was part B, that then tells us what the derivative of this function is going to be at x equals 0. So from A and B, we have the derivative is going to be the joint equal value of these things. Okay. Now, that's a lot of work, and we could do that pretty easily in GeoGebra because we could just draw the graph and just look at it. So we knew where we were going, which was great. So is that really a hard question? I don't know. I mean, some students, they see H next to a question and they freak out. They go, oh no, this is a hard question. I won't be able to do it. You can do it, okay? It's just a state of mind. So I didn't think that question was particularly difficult, but you know, it's up to you. What do you think? Is that really a hard question, or is it just conceptually difficult? Let me know in the chat. Is it a hard question? I don't know. Sometimes I get worried that, you know, these X-rated questions, some of them are quite hard, some of them are not. So anyway, I'd like to maybe we should have a new class of questions. NVH, not very hard. I don't know. I'm just putting it out there, people. I'm just putting it out there. Okay. Not very hard. All right. So let's look at implicit differentiation. So I'll go back to the PDF and I can, so we're still on in chapter 4, and I wanted to go down to this one, this implicit differentiation. Now, some of you, I'm sure, will have seen these things before. If you haven't, don't worry. These are just classic kind of problems when you're differentiating these implicit functions. Okay, so I want to just do the first one here. Find the derivative of this dy dx where y and x are related by this equation. Okay. Now, one of the tempting things here to do is try to make y the subject, and so you can differentiate. But in many of these problems, you actually can't do it. It's impossible to do. So what do we do? Well, let's have a look. So back to the document camera. So much sharing, so much clicking. So let's have a look. Question 9. So if we have the following relationship, and we sort of assume here that y is a function of x. Okay, that's sort of like hiding in the background, if you like. Okay, then what I'm going to do is I'm going to differentiate both sides of this expression with respect to x, and then I'm going to use the chain rule, okay, and whatever differentiation rules are appropriate. Okay, so one of the standard kind of steps when you're solving these problems is to differentiate both sides with respect to the variable that you're asked to differentiate to. Okay, so I know how to differentiate x cubed with respect to x, but this is a little bit more difficult. And what about this? Okay, so we can expand this because we know there's a distributive law for the derivative. Can somebody suggest how we might tackle differentiating this part? Ah, Rahul, you're on the case. Product rule, right? So the product rule is just the first function multiplied by the derivative of the second function plus the reverse, the derivative of the first function multiplied. Let me write it out. Okay, so now I'm writing much more than you usually would, but now we can get into it. Okay, the derivative of this is obviously going to be 3x squared because I'm differentiating x cubed with respect to x. Now over here it's not so clear. Okay, so what I'm going to do is I'm going to actually apply the chain rule. Okay, so the chain rule gives you the following. Now, derivatives are a little bit like fractions. They're not really fractions, but they can sort of behave like fractions. So you see I've got a d dx there, and then I've put this mess in. You can cover that up, and you've still got d dx, right? Just like in fractions. Now you see it, now you don't. Now you see it, now you don't. Now you see it, now you don't. Anyway, that allows you to differentiate this. And like you said, Rahul, you'll get 3y squared there because you're differentiating with respect to y. Okay, I can't simplify that part because it's just dy dx. And over here, if you differentiate x, you get 1. Okay, last step. Let's differentiate this. So that's going to be 3y squared, like Rahul said in the chat. So all I want to do now is simplify this and make dy dx the subject, make dy dx equal something. So here I've used the product rule. And here I've used the chain rule. Okay, so there's the chain rule there, and there's the product rule there. Okay, so let's get the dy dx's to one side and everything else to the other side. And then we'll be finished. Okay, so rearrange to obtain the following. So which way have I done it there? I'm going to take that to the other side and factorize. So I'll get 3y squared minus x. So that term's just come to the other side. I'll leave that there and push that to the other side. Okay, now just divide. And thus, let's divide out. That's it. So with those kind of questions, there usually is a standard strategy for finding the derivative. And you can see here, we started with the implicit equation, differentiated both sides, and then used the appropriate rules, including the chain rule. Lastly, move everything involving dy dx to one side. Okay? All right, we're making great progress here. Yeah, we're on fire. I know, and it's like in the morning, Rahul. I always wonder, like, is everybody watching from Sydney here or the east coast of Australia? Because sometimes I get some students who are up really, really late at night, and they're like, I don't know, they're in India or something. So where are you? Let me know in the chat where you're at. Are you in Australia? And then other students in the afternoon classes, like 5 p.m., 6 p.m., they're mostly from sort of India and Asia. So let me know. I see some people are having early starts. That's good. Yeah, it's really cold this morning, by the way. Really cold in Sydney, anyway. Oh, Rahul, you're having a late night in India. Cool. I will do a poll. Okay, let me do that. Okay, so let me I'm just going to put that in the. Okay. All right. Go. All right. So let me while you're doing the poll, let me know where you are. Let me go back to the questions. Okay. I can move that up a bit. Come back. All right. Split functions. Differentiability, continuity, and split functions. This is a classic question. Okay. This is a classic question. So I'm looking at number 12 here. And the question is, here's a function. Work out the values of a and b so that this function is continuous at 0 and differentiable at 0. Okay? So that's the question. All right. So this is like your standard kind of question for this course, and it involves limits, taking limits, and just working through those things. All right. I can see most people are in Sydney. Three people in China, one person in India, two people somewhere else. Let us know where you are. Okay. All right. So I'm going to try 12 part A. Now, let me share my document camera and I can write it all out. Okay. I remember somebody wrote Middle Earth. I'm in Middle Earth at the moment, Professor. How are you? That's great. All right, so I'm going to kill the poll now. All right, so I see most people are in Sydney. Okay, so we've got a function. And it's a split function. And it's defined in the following ways. It's a linear function when x is negative, and it's a trig function when x is greater than or equal to 0. And the question is, what values of a and b ensure or guarantee that this function is continuous at 0? And then what values will ensure it's differentiable at 0? Now, it's a bit hard to draw this curve because we don't know what a and b is, but we can kind of work it out, right? So here's your sine curve, let's say, right? Badly drawn sine curve. And then you've got a linear function over here. So I'm thinking it's sort of going to look a bit like that, okay? Because we in the first part we want continuity. I guess it can sort of look it can go sort of there or whatever. It has to join up at 0, right? But also in the second part we're going to want to get a nice smooth connection here, okay? So we can kind of get some idea of what's going on. But let's do it algebraically, okay? So I might just start back over here to save a bit of space and get it all on one page. So for 12 part 1, we want to find the values of A and B such that this limit condition is satisfied, and this is exactly the condition for continuity at 0. Okay? So what is f of 0? If we go here, x equals 0 here, so f of 0 will be sine of 0 equals 0, right? You can also work that out from the graph. Let's look at the right-hand limit. Okay, so as we come in from the right, that's going to be our function. And that's also going to 0. So it's looking good there. We haven't actually found A or B yet. Let's come in from the left. Okay. So that's going to be AX plus B. So what values of A and B will ensure that this is going to be 0? Well, A could be anything, but who can tell me in the chat, what do you know B has got to be? Yeah, B equals 0. Okay, thank you, Dharam. We're not quite sure what A is yet because this limit will be 0 for any value of A, so we're not quite sure about that. Okay. So we've kind of solved part of the problem here. So let's go on to part 2 where they say, well, what about differentiability? Okay. Part 2 will actually allow us to get this value of A. We know B's got to be 0, but A also isn't found yet, right? We don't actually have enough information here because, like I was saying before, you could have a curve that just looks like that, and it would satisfy the conditions of continuity. So let's look at this. The derivative at x equals 0 is defined in the following way. Now I'm not using h's in this. I'm just using this definition here. Okay, and so let's consider this from the right and from the left. Just similar to what we did over here. So this is our, if this limit exists, that's the condition for differentiability. So let's come in from the right. So what are we going to get up here? We're going to get our x is positive, so we get our sine function. Okay, that's 0, that's 0. What is the limit here? Who can tell me? Anyone? Who can tell me? What is the limit of sine x on x as x approaches 0 from the right? Yes, thank you. This is just 1. Now, if you wanted to do that, you could apply L'Hopital's rule if you wanted to, or you can probably just state it. Okay, if you wanted to do it using L'Hopital, you differentiate the top, differentiate the bottom, you get cosine, no worries, right? Okay, so let's work with the other part now, where we approach from the left. Okay, so now x is negative, so we're working with this function, at least in here. F of 0 is sine of 0, which is 0. All right, so now the question is, that's 0, that's 0. If I take this limit, the b on x, that's going to go to infinity. So do we know anything about b? What does b have to be? What value of b does has to occur here? Yeah, Oliver, you're on the case. Julia, thank you. Because we've worked out the continuity here, b has to be 0 because we're going for differentiability, right? So we actually get something like this. That disappears from part 1, and we get this. Okay, the x's cancel, and we get that. So we want this limit to be equal to this limit. Yeah, Rahul. So a equals 1. So let me see if I can just squish it. A equals 1, b equals 0. Squished it in. And if you look, that's kind of what you would sort of expect from this graph anyway, right? If you want that nice smooth transition, you know, you've just got a basic function there, the y equals x or something. Okay? So these kind of questions, they're classic Math 113 examples where you work out the continuity first and you get one of the conditions usually, and then the differentiability gives you the other, and you use this in here. Okay? I actually think that's harder than the previous one that we did, but you know, that's up to me, up to you really. All right. All right, I wanted to talk a little bit about the mean value theorem, okay? But I guess I'll do one of the related rates questions first, okay? Because they're always a bit tricky. Okay, so let me do this one quickly. I'll just find it on my PDF. Okay, so I'm going to stop that share, and I'm going to go back to the PDF. So you probably, some of you may have seen these kinds of problems at school. The related rates questions where you're using the chain rule to solve a problem. Okay. So I'm going to do 15. It's just a standard one, and you've got an equilateral triangle, and the length of the sides are increasing at a certain rate. And the question is, how fast is the area increasing? Okay, so with these kind of questions, I tend to like to draw pictures. So let's see if we can put that into a picture somewhere. Okay, Logan, a equals 1 in the previous question because the left-hand limit and the right-hand limit have to be equal. Okay, so let me just go back there. It's a good question, right? So this limit only exists if the right-hand and the left-hand limit are both equal. We worked out the right-hand limit, it was 1. We worked out the left-hand limit, it was a. In order to get this limit existing, these two things have to be. Okay, does that make sense? Logan, let me know, buddy. Yeah, so these things have to be equal. Otherwise, this isn't defined, right? And this doesn't make sense. Well, if you cancel off, Marley, if you cancel off the x's, what are you left with? You're left with a constant, and the limit of a constant is just a. Yeah, you got it. Yeah, there is another function called the split value function or something theorem. Split function theorem. Is that it? Does a split function theorem ring a bell? Is that in your notes? Because that used to be in this course, and you would do the piecewise differentiation, like Justin's saying in the chat. Okay, I'm not sure if that's actually still in the notes. I don't think it is, but it might be. Okay, so here's one that I've done earlier. So I'm just going to plonk this up on the screen here because I want to get to the MVT. Let me see if I can zoom in a bit. Oh, hang on, let me do this. Bump, bump. Aha. Here I go. Yeah. All right, everyone. This is from my private stash of solutions. They're from about like 8 years ago. All right. Paolo, it's a good question about the previous problem. I wouldn't use, it's a bit dangerous with just differentiating and inserting x equals 0 because there are some functions where that won't work, and it won't reveal any information. Okay, so just be careful. Just be careful. Yeah, so it comes with a warning, Paolo. I hope that makes sense. The best way is to use limits, but I know some people don't like limits. Some people want to learn calculus without limits. Yeah. All right. So in this problem, you've got an equilateral triangle, and you're told that the length of the sides are increasing at r centimeters per second, right? And the question is, what is the rate of change of the area? So I've drawn in my equilateral triangle, and I've worked out the area. It's, of course, half the base times the height. And the height, because that angle is 60, can be written like that. And sine of 60 is √3 on 2. So first step, get a function for your area. And we want to compute dA dt. Now we're going to use the chain rule for that, yeah? So let me zoom out a bit. And I can go back all the way. And you can see here the chain rule's just this product of derivatives. Okay, it was easy to get that. D big A, D little a, no worries. But I want dA dt. So I'm given this bit of data. By the chain rule, I get that. Multiply this with this. Okay. So not a super difficult question there, but you're just using the chain rule, and you've got to realize, well, I don't have that in terms of t, so I need to do something here to get it, the derivative in terms of t. Okay. So there you go. All right, I wanted to talk quickly about the MVT. You down with MVT? Yeah, you know me. So let me show you what the MVT is all about. Okay, anyone still going with that one? I'll just finish up, and I will show you the mean value theorem. It's not mean. It's a very nice kind of theorem. Okay. So let me just go through to the questions on my PDF. Just give me a sec. Oh gosh, it's the longest chapter ever. All right, here we go. So I'm going to stop sharing there, and I'm going to share my PDF. All right. It's so clunky, the sharing. It's like clunk, click, clunk, click. Okay, mean value theorem. What does the word mean here? Okay, mean equals average. Oh, yeah, angry. Yeah, mean value. So the mean value theorem equals average value theorem. That's what it means. Yep, the RAM X bar. Angry Marley. Yeah, they could be getting angry, like the cross product, right? But what does it actually say? Well, probably the best way to illustrate it to you in a informal way is just to draw a picture. So, you know, did someone say GeoGebra? Let's look at this function here, root x on 0, 2, and I'm going to put up a GeoGebra picture, and all will be revealed. Okay, so here we go. All right, so I've got a function, root x. Now, really, I'm just interested in the interval from x equals 0 to x equals 2, but I've just drawn the whole thing in there, okay? It doesn't make a difference. All right, so what I've done now is I've gone, okay, that's the line connecting this point with that point. Okay, so at x equals 2, I've got a point, and x equals 0, the endpoints of the interval. I've basically just drawn a line or a line segment connecting those 2 points. Okay? So what the mean value theorem says is that there is some point between 0 and 2 where the slope of the graph is parallel to this black line. Let me say that again, right? The mean value theorem says that, for example, in this graph, there's a point in between 0 and 2. It's actually this point here, okay, 0.71, where the tangent line to the curve is the same slope as this line here. They're parallel, okay? They're parallel. That's pretty much all it says, okay? So you go to about 0.71 here, and the tangent line there is the same as the slope of the tangent is the same as the slope of this line. That's it, they're parallel, okay? So pretty much you can explain the ideas in the conclusion in the mean value theorem just through a picture. It's super easy, okay? All right, so how do you do these problems by hand? Well, I'm glad you asked. Let me have a look at one part B. So this is now chapter 5. So let me share my screen with you. And we can quickly do that one. All right, so this is one part B. So I've got a function which is root x, okay? So I'm defining it to be that function there. And the question asks us, find a number C which satisfies the conditions of the MVT. Okay, so let's work out what that means. So the conclusion of the MVT, we're not interested in the conditions yet, that's a different kind of thing. It says there is at least one point C, which is strictly between 2 and 0, such that, ST stands for such that, the derivative, or the slope of the tangent line, is equal to this slope or gradient. Okay? So let's work these things out and find a C. Find a value of C. Okay. So I guess I can work out the right-hand side first. Okay, so f of 2, it's going to be root 2 minus root 0 over 2 minus 0. So if you simplify that, you'll get 1 on root 2. Also, let's work out the right-hand side. So we differentiate. So we differentiate that, we'll get 1 on 2 root x, and we want to evaluate that at x equals c. So now we want to, because we're trying to solve this equation for c, we let this equal this and simplify. So let's solve the, okay. So we can rearrange. So we can get root c equals root 2 on 2, which is just that. So c equals 1/2. Okay, so is that between 0 and 2? Yes. Okay. So let's go back to our picture for a second. I'll come back to this in a sec. I just want to show you what's going on here. So if we go to 1/2 here, about here, right? X equals 1/2. The slope of the tangent line there is the same as the slope of this other line. Okay, so they'll be parallel. If you run a tangent to the curve at 1/2, then you'll get another parallel line. Okay, and I'll just put my document camera back up for a second. Okay. Now you can use the mean value theorem to do all sorts of interesting things. If you look at, for example, question 5 from this chapter, then, or question 4 even, then they use MVT to prove all sorts of, cool inequalities and all sorts of stuff, relationships. But we don't have time to do those, but I will do those later in the week. So if you want to have a bit more of chapter 5, then I'll probably do some other questions later in the week when they can be recorded and whatnot. Okay, folks, I am going to head off. They are, so the other tutes, Marley, let me just have a look. Tuesday, 3 p.m. Sydney time, and Thursday, 3 p.m. Sydney time. So Tuesday, 3 p.m., Wednesday, 3 p.m. Come on, come all. It'd be good to see you again. Yeah. Darren, sometimes it's a good question. Are your other tutes the same questions or different? Sometimes I do the same questions, sometimes they're different. I just like, because they're all recorded, I don't always like to record the same questions, although I need to admit something. In Monday, sometimes I'll say some stupid things, and then by about Thursday, I'll say much better things in the tutorials. That's just part of being human. So yeah, if you want to watch the lectures or the recordings of my tutorials, then that's great. Yeah, Osman, thanks. I think it's very normal for tutors to make a real impact on the students, because that's actually where you get to know students and they get to know you. In lectures, it's huge, right? It's easy to get lost. So if I can help, I'm very happy to help everyone. I know it's hard to really get the good value out of lecturing sometimes. All right, folks, I'm going to head off. Enjoy the day. Hey, we got some new mates. Did you see my new mates? We got the Yoshi brothers in today. So yeah, I'm gonna head off, and I will see you. Yeah, Yoshi. Just enjoy and good luck. Good luck with the lab test. You can do it. Get 100%. Get 20 out of 20. Okay. I'll see you later, folks. All right. Bye, everyone.